Collisions. You might get wiped out by a professor or something.
What? Yeah. He bought some gift cards, but he didn't actually send them anywhere. He's going to use them himself because he started getting suspicious about it.
Oh, I see. So
I think so. Yeah, that's my impression. We only got
I don't know. Nobody's ready to be live.
stupid person. You said he got it.
It's really good.
Which is different.
I can feel like I'm a meteorologist or something like that.
Same thing. She just
You mean about the regular observations?
Yes.
We're good whenever Hannah.
We're ready?
Good to go.
Okay. All right. Welcome to the first colloquium of the spring semester, my friends. Okay, so it's my great pleasure to introduce Patricia DeRepentigny. Sorry, Pat. I know. I do my best.
That was very good.
I've known her for a long time and still can't pronounce her last name well because French is just not my strong suit.
So you shouldn't feel bad.
Don't cringe. Anyway,
Forget to unmute too.
Patricia goes by Pat typically. So Pat is an advanced study program postdoctoral fellow at the National Center for Atmospheric Research. She's been in that role since 2021 now, almost at the end of that. Her research kind of focuses on future projections of Arctic sea ice, diverse system models, with the general goal of improving our understanding of how multiple drivers of sea ice retreat are impacted by sort of seasonal to century timescales, all sorts of awesome things like that. She got her Bachelor of Science in Earth and Atmospheric Sciences at the University of Quebec in Montreal. I'm not saying that in French. A Master of Science in Atmospheric and Oceanic Sciences from McGill. And then in 2021, she got her PhD in Atmospheric and Oceanic Sciences from the University of Colorado Boulder. And that's where I met her when I was postdocing at the time. So Pat has a really ridiculous history of understanding all things Arctic sea ice, that she's been wanting to do that since she was a kid. And she has definitely made good on that promise to herself. And she's got all sorts of other really nifty things to her name as well, including the CSM Graduate Student Award, which is an award that we give out for the Community Earth System model for graduate students that made really important contributions to that climate model, and she won that a couple years ago as well. She'll be moving off to her second postdoc in Belgium at some point in the hazy future. So that's a really big deal. But today she's going to be talking about the role of aerosol emissions in the early 21st century, simulated Arctic sea ice loss. So Pat, take it away.
Thank you for the great introduction. Hi everyone, thanks for joining today. It's really nice to see a full room. And I'm really happy to be here today. I feel like I've given a few invited seminars since I graduated, but it's been in the COVID era, so most of them have been virtual, so it's great to be here in person today. So like Hannah mentioned, my name is Patricia DeRepentigny. I'm an ASP postdoc in the Climate and Global Dynamics Lab at NCAR. And today I want to talk to you about the role of aerosol emissions in the early 21st century simulated Arctic sea ice loss. And most of the results I will be presenting today are from this publication listed at the bottom here in Science Advances. But I will also be sharing some preliminary results that kind of follows from the work in this paper. So I wanted to start by telling you a little bit about me, in case you don't know me, because I feel like I don't know a lot of you. So I grew up in the town of Gatineau in Quebec in Canada. Gatineau is actually on the Quebec side, but it's just across the river from the capital city of Ottawa. So you can see this picture here is taken from the top of the Parliament in Ottawa, and then Gatineau is on this other side of the river, which is why my name is so French. I then moved to Montreal, where I did my Bachelor's of Science and majored in meteorology at UW. And then afterwards, I moved to McGill University, which is literally just a block away from UW, where I did my master's in atmospheric and oceanic sciences. And this is where I started working on sea ice modeling with Dr. Bruno Tremblay. After that, in 2017, like Hannah mentioned, I moved to Boulder to do my PhD at CU Boulder, working with Alexandre Yan and continuing this work on Arctic sea ice. And then recently, I started my postdoc at NCAR, again, just around the corner, up the hill to the Mesa Lab. If you've never been, it's really beautiful. So yeah, this is kind of where I am right now. Okay, let's get into it. So, as we all know, the Earth has been warming since the start of the Industrial Revolution, but the warming has not been equal everywhere. The Arctic in particular has been warming at 3 to 4 times the rate of the rest of the globe, as you can see by these warmer color here in this map. You can also see in the bottom figure, this is showing you a zonal mean of the warming. You can see that it's really more pronounced north of 60 degrees north. And a consequence of this warming has been the loss of Arctic sea ice, with large decline across all months of the year. So this figure is showing you the extent of Arctic sea ice as a function of time per month here. And you can see that all the months have lost a lot of sea ice here. The earlier decades are shown in the lighter shades of pink, and the more recent decades are shown in the darker shades of pink. So we've really lost sea ice across all months of the year, but the largest decline that we've seen has really occurred at the end of the summer in September. And you can see in these maps that are showing you the extent of summer sea ice in September 1979, which is the first year that we had satellite observations in the Arctic, compared to September of 2020, how much ice we lose at the end of the summer. And just to put that into context, the amount of ice that we had at the start, at the end of the summer, at the start of the satellite observations, is about the same as the area of the contiguous US. And by comparison, the amount of ice that we've lost since is about 4.1 million square kilometer, which is about equivalent to the area of these states shaded in red here, so a pretty large area of sea ice that we don't have anymore at the end of the summer. So another way to look at this decline of end of summer sea ice is to look at a time series of observed Arctic sea ice area at the sea ice minimum in September from 1979 to 2022 from NSIDC. And I've added the blue line here, which is showing you the linear trend over the whole observational record. In addition, I've added the pink line here, which is showing you the trend from 1996 to 2007, and then in cyan, another trend showing you the trend from 2008 to 2022. And what you can see is that over the period showed by the pink line, the trend in sea ice decline was larger than the overall trend. And that since 2007, the trend has been smaller than the overall trend, which is indicative of a reduced rate of Arctic sea ice loss. And so this acceleration, followed by the reduction that has already been reported in the scientific literature, and a lot of papers have shown that internal variability can explain these periods of high and low trends in Arctic sea ice decline on decadal timescales. Okay, now I'm going to give you the classic slide of why the sea ice is important. So sea ice is really a critical aspect of the Arctic Ocean system. It increases the albedo of the surface compared to the open ocean, reflecting a large portion of the incoming solar radiation that would otherwise be absorbed by the very dark open water. It regulates the exchange of heat, momentum, and moisture between the atmosphere and the polar ocean. It also impacts the freshwater balance and circulation of the Arctic Ocean and the global oceans. It provides hunting and breeding grounds for polar bears and ring seal and a bunch of other species. And it also acts as a source of food and transportation for indigenous communities, just to name a few reasons why sea ice is important. So as temperatures are predicted to continue to rise under increasing greenhouse gas concentration, Arctic sea ice loss is, was that me? I don't know. No, on hell.
It was notifying me of you.
Well, you're here, so there we go. We're good. So yeah, Arctic sea ice loss is predicted to continue. And so these figures are showing you the evolution of global temperature anomaly in a variety of CMIP6 models across the 20th and 21st century. And so even though there's quite a large spread across these models, overall they all suggest that the globe will continue to warm, and as a consequence, sea ice here, this is showing you evolution of September Arctic sea ice area is going to continue to decline. Again, there is a very large spread until they reach ice-free conditions. Okay, so for this study, I'm going to be focusing on the CSM model, or Community Earth System Model, which is developed at NCAR. And this plot is showing you the evolution of September sea ice area in the CSM1 large ensemble, which has 40 ensemble members here indicated in parentheses. And I don't know if you can really see the shading. It's a bit pale. It looks better on my screen. But anyways, the shading here that you can sort of see in orange is showing you the range of internal variability that is simulated by this large ensemble. And then the thick line is showing you the ensemble mean. So now I'm going to add another line which is showing you the same sea ice evolution, but for the CSM2 large ensemble. So the CSM2 large ensemble is the most recent version of the CSM model. And it's also a large ensemble with 50 ensemble members. And the first thing that you can see is that these two models simulate completely different sea ice evolution in the Arctic. First of all, they don't start around the same point, and then the rate of decline is also very different. And so just to recap, I'm going to put this table a few times throughout the presentation, but we have the CSM1 large ensemble, which uses the CSM1 version of the model and CMIP5 forcing. And the CSM2 large ensemble uses the CSM2 version of the model and CMIP6 forcing. So there are two main things that vary between these two sets of large ensemble, not just the model version, but also the forcing that is used to drive this model. In addition, I've added this pink line, which shows newly available simulations that are called CSM2 CMIP5. So as the name implies, those use the CSM2 version of the model with CMIP5 forcing instead of CMIP6 forcing. And we have an ensemble member an ensemble size of 10 here. And so with these three sets of simulations, we are able to quantify how much of the difference between those two initial large ensembles is due to changes in model version and how much is due to changes in forcing. And so what you can see on this plot here with the purple line that I've added is that at the beginning, the two simulations that are run with CSM2 have a very similar evolution of Arctic sea ice with a very similar mean state. And so because of that, we can say that the difference between CSM1 and CSM2 at the beginning is really due to changes in model version and not changes in the forcing. However, when we get to this first vertical line, which I'll explain in a little bit, you can see that the purple and the black lines start to diverge. And so I've plotted this in terms of anomalies here just to make it a little bit easier on your eye and to be able to really notice these differences in the rate of decline. And what you can see here is that the purple and the orange line really follow each other. So the rate of decline with the two versions of the model that use CMIP5 forcing are very similar. Whereas this black line, which uses CMIP6 forcing, the sea ice declines a lot faster, and then it has this kind of like recovery for a few years around year 2020. And so again, with these three sets of simulations, we're able to say that the difference in the rate of Arctic sea ice loss here is due to forcing differences and not to model physics. Another way to look at this here is just, this is showing you the sea ice area trend. So these are 20-year linear trends with the end year of that 20-year period plotted on the x-axis. And again, you can see that at the beginning, the three simulations have very similar trends around 0. And then around this first vertical line here, the two simulations with CMIP5 forcing have a very similar decreasing trend or increasingly negative trend, if you will, until it starts to diminish, whereas the CSM2 has it reaches this really large negative trend, and then after that there's this like rebound that goes back to neutral, slightly positive trends. So what has changed from CMIP5 to CMIP6 that could explain this difference in the rate of sea ice loss? And we found that one important difference between CMIP5 and CMIP6 has to do with biomass burning emissions, which I abbreviate to BB emissions in the text. So biomass burning emissions are emissions of gases and particulates from the burning of live or dead vegetation that can affect the climate through cloud aerosol interactions. And estimates of biomass burning emissions that are used to prescribe the forcing in our climate models, they come from a variety of sources. However, starting in 1997, these estimates are based on the Global Fire Emissions Database, or GFED, which combines newly available satellite information on fire activity and vegetation productivity to provide a more realistic picture of biomass burning emission. And so this is what these two lines here indicate the period where we use this GFED data set. In CMIP6, the biomass burning emissions were updated to include interannual variability instead of only using decadal means, which is what was done in CMIP5. And so you can see in these figures that are showing you time series of biomass burning emission. This one on the left is for the northern hemisphere mid-latitude, and the one on the right is globally. You can see that in CMIP5, we basically had one value for each decade and kind of did a linear interpolation between those different values, whereas in CMIP6, we have variability from year to year, so these little bumps ups and down, but what you can see is that this results in a really big increase in the variability at the start of the GFED period. There's actually about a 5-fold increase in the standard deviation compared to pre-GFED years over the northern hemisphere mid-latitudes. Okay, so to look at the impact of this increase in biomass burning variability over the GFED period, I designed some sensitivity experiments, which I refer to as CSM2BB, and they're shown in green here. And in these experiments, we averaged the biomass burning emission over the GFED period from 40 to 70 north, and we used a fixed annual cycle to, again, remove that year-to-year variability. So there's still a seasonal cycle in the biomass burning emissions, but it's always the same year after year. And we made sure to conserve the total integrated amount of biomass burning emission over that same period so that we didn't have a difference in the amount of emissions that we put in the system. And so this is represented by the green line here in this plot. And the emissions pre and post GFED are exactly the same as in CMIP6. And so as a result, you can see that the emissions over GFED are actually more similar to CMIP5. So the green and the orange line are almost on top of each other. They're not exactly the same, but they're getting pretty similar over GFED. We do this only from 40 to 70 north because we really want to isolate the impact of northern hemisphere mid-latitude wildfires on Arctic sea ice. And in the figure on the right, you can see that the global emissions are almost unchanged in the CSM2BB. So in the green line, they're almost the same as the black line. And that's because northern hemisphere emissions only make up about 14% of global emissions. So it's a pretty small contribution. Yes?
Do you know how much non-mid-latitude smoke makes its way to the high latitudes in your model?
Well, I was just going to say that we, no, that's a good question. But I was just going to say that we did similar experiments where we averaged the biomass burning globally instead of only from 40 to 70 north and got exactly the same results. So this really highlights the impact of those northern hemisphere mid-latitude wildfires. And kind of to answer your question, it seems like there's very little emissions south of 40 degrees north that make it to the Arctic. Yes?
Just to follow up, you were saying that you still resolve the seasonal cycle.
Yes. It's not shown in here.
Yeah,
There's
okay.
a 12-month running mean on this plot.
There's a 12-month running.
Yes, that's
Okay,
correct.
thank you.
Okay, so just to recap, I'm bringing up this table again. I've talked to you about these first three sets of simulations, CSM1 large ensemble, CSM2 CMIP5, and CSM2 large ensemble. And now we have the CSM2BB, which uses the CSM2 version of the model and CMIP6 forcing except for biomass burning emissions from 1997 to 2014 and also from 40 to 70 north, I should have mentioned. And we have an ensemble size of 10 for these ones. Okay, so now I've set the stage. What did we found in the sensitivity experiment? What is the Arctic and temperature and sea ice response to that change in biomass burning variability? So we start with variability in biomass burning emissions over the northern hemisphere mid-latitude. This is the same figure that I've shown you before, but just highlighting the two sets of simulations here. And what we found is that this variability in emission translates into variability in biomass burning aerosols in the Arctic. And so what we see is that these emissions produce aerosols, these aerosols get transported to the Arctic, and we see that same variability in the amount of aerosols that are in the atmosphere over the Arctic. Okay? However, these aerosols, when they're emitted, they're called fresh aerosols, and at the beginning they're hydrophobic, so they can't interact with water. So they need to go through some chemical processes of aging until they become hydrophilic, and then they can act with water vapor to form cloud condensation nuclei. After that happened, what we found is an increase in cloud droplet number, as can be seen in this figure here. So this map is showing you the vertically integrated cloud droplet number, and this is the CSM2BB minus the CSM2 large ensemble, or the experiment minus the control, if you will. And you can see this very large increase in cloud droplet number, especially over land in the northern hemisphere mid-latitude where the wildfires are occurring, because wildfires are not occurring over the ocean, over the Arctic. But you can see that there's also this big increase over the North Pacific and also over the Arctic here, or even in the North Atlantic. With increased cloud droplet number, we also see an increased cloud optical depth. And as a result, we see decreased shortwave radiation reaching the surface. And so this plot here, similar plot, is just showing you the difference in net surface shortwave flux. So again, you can see these very dark blue colors here. So less shortwave reaching the surface in the experiment, in the CSM2BB experiment. As a result, we see surface cooling in the Arctic, and so this first plot here is showing you the evolution of Arctic temperature anomaly, and you can see our simulations here that starts in 1999, and even though the Arctic is still warming over the GFED period, it's not warming as much as it did in the CSM2 large ensemble in black here, and you can also see this in the maps at the bottom here. These are maps that are centered over the North Pole, if you're not used to looking at polar oceanographic maps. But you can see that in the CSM2 large ensemble, the trend in surface air temperature is really large. You have this really like dark red bullseye right over the Arctic Ocean, and you can see that it is a lot more muted in the CSM2 BB, so less warming. And as a result, we also see less sea ice melt. And so, again, this is just showing you the evolution of sea ice area anomaly, and you can see that the sea ice melt that was really pronounced here in the CSM2 large ensemble is just more muted in the CSM2 BB here in green. And again, you can see these in those maps where those really dark blue colors of negative trend in sea ice concentration are a lot less dark blue in the CSM2 BB here. So you might be wondering, Patricia, how does removing the variability, so removing years with high and years with low, can result in this overall increase in cloud droplet number, surface cooling, and less sea ice melt, right? You would expect that variability would use some years with more cooling, some years with warming, right? And that is because I've skipped an important process in this diagram here of nonlinear cloud processes that are linked to cloud aerosol interaction that I will explain now. And so there's been some work, recent work that have highlighted how aerosols can impact Arctic climate and how the sensitivity of aerosol-cloud interaction to the rapidly changing sea ice state is changing with time. So this is what this paper is showing here, looking at the change in sensitivity as the Arctic changes. So these aerosol interaction, or as I put it on this slide, how fire impacts ice. At the same time, there's been another study that have shown that the reduction in Arctic sea ice can lead to atmospheric circulation changes that create more favorable conditions for large wildfires over the western United States. And so there's really this kind of two-way interaction between fire and ice. And for the next slide and the rest of this talk, I will be focusing on this part, so the impact of these cloud aerosol interactions on the sea ice. But it's important to remember that this is kind of a two-way street, and both can influence each other. Okay, so I've brought back this figure. I've just zoomed in a little bit on the GFED period. This is just the biomass burning emission in CMIP6 as well as in the CSM2BV. But again, I've zoomed in so that you can really see the highs and the lows a little bit better. And the next few plots that I will be showing are these vertical time series, if you will. So you have pressure on the y-axis, or you can think of this as height. So as a function of height. And then we're going through time here, and the vertical line in all these plots is showing you the start of the GFED period, so when that variability really starts to increase. And note that these are summertime averages, so June, July, August. And those are going to be difference plots that are going to be showing you the CSM2BV minus the large ensemble, or the experiment minus the control, if you will. And so, just to make this a little bit easier on your eye, because I've stared at these plots for a really long time and you can start to see a lot of things, I've added some lines here to indicate, so the red lines are showing you years where you have more emissions in the experiment than the control, and the blue lines are showing you years where you have less emissions in the experiment than the control. So what you can see in this emission plot at the top here is you kind of get this pattern of like red, blue, red, blue, red, blue, red, blue, okay? And you can see that this matches pretty well with this first plot that is showing you aerosol in the primary carbon mode. So again, these are these fresh aerosols that are hydrophobic, that make it to the Arctic, but cannot interact with water yet to form clouds. And so again, we see this red, blue, red, blue, red, blue, blue pattern. So that's how we can say that this variability in emission is translated into variability in biomass burning emissions in the Arctic. Now the second plot here is showing you the number concentration of aerosols in the accumulation mode. So these are these age aerosols that can now interact with water to form cloud condensation nuclei. And what you can see is that we've kind of lost our red, blue, red, blue, red, blue pattern. So we only see those red peaks, but it seems like the blue years are gone. And so we think that this asymmetric response is likely a reflection of the nonlinear and saturated response of CCN to aerosol loading. And what I mean by this is that in the red years, we start with a very low amount of emission, and then compared to the experiment, we add a little bit more. But then in the blue years, we start with that little bit more, and then we add even more of that. And at one point, the system becomes saturated, and adding a little bit of aerosols when you start with a very low amount makes more of an impact than if you start with a relatively high amount and you add even more aerosols. So at one point, the system becomes saturated. So this is what I mean by non-linear processes. As a result, we see that the cloud droplet number, again, those red years are really showing up as being important, whereas the blue years, we don't see that much difference in cloud droplet number. We also see an increase in cloud liquid amount. I will mention that there's very little change in the cloud ice amount. Note also that these are summer averages, so most of the clouds in the Arctic in the summer are mixed phase clouds, and it seems to be affecting the liquid amount more than the ice clouds. We also see, again, these red years in the cloud optical depth. And finally, we see temperature decrease throughout the column as well as at the surface. Okay, I wanted to mention, since I've mentioned CMIP6 at the beginning, that we also find similar indication of a sea ice response to this increased internal variability in some other CMIP6 models. So similar to the CSM2 large ensemble, which is at the bottom here, these are showing you again sea ice area trends, and you can see the CSM2 large ensemble that reaches these really large negative trends. Well, there are some models that do seem to simulate an acceleration in the trends towards highly negative values, not as much as the CSM2, I will point out. But there seems to be an indication that some models have this like acceleration in the rate of sea ice decline over the GFED period. However, there are a lot of other models, those are the ones in teal, that do not seem to show any sensitivity to that increased variability in biomass burning emission, which indicates that there's really a large contribution from model uncertainty in this response to a specific forcing across CMIP6 model, and that could potentially be explained by differences in how aerosol-cloud interactions are simulated in the model. So again, coming back to that piece of model uncertainty. Okay, now I want to come back to this first plot that I've shown you with the observation and ask the question, what do our results mean for understanding the evolution of observed Arctic sea ice loss? So as I mentioned earlier, there's this kind of like steepening of the trend, and more recently it's been more of a flat trend. And this qualitatively matches what we see in the CSM2 large ensemble. And so again, this is showing you the sea ice area trend. The observations are in red, and here, instead of showing you the range of the large ensemble, I'm showing you each ensemble member, each 50 ensemble member of the large ensemble, because we're comparing to observations, so we need to compare one member at a time. And what you can see is that the observations have this kind of like V shape in the trend, so they have trends that get larger and larger until about 2010, and then the trends then get smaller afterwards, or less negative, if you will. And you can see that that V shape is also simulated by all 50 members of the CSM large ensemble. And so this kind of leads us to think that maybe there's a force response here that is linked to that biomass burning that can explain this behavior of why we had the steepening and then the recent reduction. In contrast, if you look in the 10 members of the CSM2BB here, we really don't see a coherent response across all the ensemble. So some of the members do have a little bit of a V shape, if you will, but some really don't. They kind of have the opposite of a V, they have kind of an A shape. So we don't really see a force response here in the ones where we remove the variability. So this kind of leads us to think that maybe there's a potential for the role of biomass burning emission in the observed Arctic sea ice loss since the late 1990s. However, if you look, these bottom plots here are showing you sea ice area anomaly, so just the evolution of Arctic sea ice, and you can see that the observations here fall within the range of the CSM2 large ensemble as well as the range of the CSM2BB. And so internal variability is just really too large for us to be able to answer this question and really say with confidence that the biomass burning variability has been explaining these trends in observed sea ice loss. However, our results do indicate that the biomass burning variability can strongly influence multi-decadal transantarctic sea ice, so this should really be investigated further, and there are some people that are currently working on that. I just wanted to highlight, this is some of the work that Kyle Hedblum conducted, also looking at the impact of this increased variability. He actually looked more at the impact on the hydrological cycle, so I just wanted to highlight some of the results that he found. But basically, and I apologize, his plots, he's showing the CSM2 large ensemble minus the VV, so the control minus the experiment, whereas I've been showing you experiment minus control, so just flip things in your head. But basically, we see some changes in the hydrological cycle from the simulations that have smooth variability versus high variability. So we see a reduction in total precipitable water, total precipitation, and relative liquid precipitation. He also found there's some changes in ocean heat content in the northern hemisphere, in the top part of the ocean, and changes in the energy transport that are mostly due to changes in atmospheric energy transport, which is this kind of like ugly green line there. Okay, so to conclude, I've shown you that the CSM2 large ensemble simulates an acceleration in sea ice decline that coincides with the start of the GFED period. And then we conducted sensitivity experiment where we removed this interannual variability, and we found that the sensitivity runs show reduced Arctic warming and sea ice decline compared to the CSM2 large ensemble when we removed that biomass burning variability. The reduced biomass burning variability leads to enhanced cooling due to summertime nonlinear aerosol-cloud interaction, as increased cloud optical depth during years with low aerosol burden enhance cooling more than years with high aerosol burden. So there's that nonlinearity piece that's coming in here. There are also indication of a biomass burning force signal in the observed early 21st century sea ice loss, but again, the significant role of internal variability does not allow us to conclude that this is caused by the biomass burning variability. So what's next? I said I would present some preliminary result that followed from that. So one of the questions that I think follows pretty logically from this study is what are the other forcings that have changed between CMIP5 and CMIP6, and what is their impact on climate? Throughout this whole talk, I've focused on biomass burning emission, but there are a lot of other forcings that have been updated from CMIP5 to CMIP6, and clearly those could have a really big impact on the climate as well. So I'm bringing back this figure that I've shown you at the beginning, and just to show you, I've also added the CSM2BV here in green, and what you can see is that this difference here in the rate of decline between CSM2 with CMIP5 and CSM2 with CMIP6, and that's where the CSM2BV falls. So it falls about halfway in between CMIP5 and CMIP6. So we can say that the variability in biomass burning emission explains about half of that difference, but there's clearly another half that is due to something that has changed. So this is something we're looking into. Another way of looking at this, this figure is showing you just the anomaly, sea ice area anomaly between CSM1 large ensemble and CSM2 large ensemble. And again, with these CSM2 CMIP5 runs, we're able to quantify how much of the uncertainty is due to model differences, how much is due to forcing differences. And what you can see is that the model difference in black is pretty small up until way into the 21st century. But the forcing uncertainty, which is also relatively small at the beginning, kind of dips and becomes like really large. So this is that aerosol uncertainty that I've been talking about. And you can see that we've also separated the biomass burning forcing. So this is that biomass burning variability that I've been talking about. And you can see that it explains about half of that total forcing uncertainty and that difference between those two large ensembles. Interestingly, the rebound that we see here in the CSM2 large ensemble in that blue line seems to be mostly explained by forcing, but not biomass burning forcing. As you can see, this dark blue line is almost zero, whereas it seems to be mostly driven by the rest of the forcing and maybe a little bit of model differences. So this is something that we're looking into a little bit more. And one way to look at this is we're going to be using those newly available CSM2 single forcing runs. So these are runs that Isla Simpson has conducted at NCAR, and these are runs where, for example, only anthropogenic aerosols are evolving and all the other forcings are fixed at pre-industrial level. And we do this for anthropogenic aerosols, we do just this for greenhouse gases, for biomass burning, and for everything else. And so with that, you only have one forcing that is evolving, so you're able to better quantify what is the effect of that change in the forcing on the system. Okay, the sensitivity of CSM2 to changes in biomass burning variability also raises the question as to whether the lack of internal variability in aerosol forcing in the pre-industrial and in future scenario, it could be problematic. So how does our choice of fire emissions, and I would add to that any type of other aerosol forcing, in the pre-industrial, historical, and future climate affect our simulation of climate variability and change? So we have an idea of what is the natural internal climate variability of our model, but as I've shown, these are usually based on pre-industrial control run where there's very little variability in these emissions. So do we have to rethink our estimate of the internal climate variability in our simulations? Finally, how does the variability and change in fire emission affect the evolution of sea ice, including the main state, the trend, and the variability? And to answer these last two questions, we have climate simulations with an interactive fire model, where the model itself, there's dry conditions and then it starts a fire by itself instead of being prescribed, where when we tell the model there's a fire there at this time. So we have these runs with an interactive fire model that are underway. They're not quite ready yet. It turns out it's very challenging to represent fires in a model in an accurate way, but some very bright people are working on this at NCAR at the moment. And so with that, I will stop. I'm happy to take any question, and I will mention that I'm here for the rest of the week, so if any of you want to talk, just reach out. I'd be happy to talk more about this or any other thing. So thank you very much.
All right, graduate students, start with some questions. Yes,
I had a question about just a little bit more detail about exactly how the biomass burning is represented in the models, like before and after this period of high variability.
Yep.
Is there any zonal variability, like in where the emissions are coming from, or is it just kind of put a forcing everywhere?
Yeah, let me get the figure once I find it. Yeah. So yes, in CMIP 5, we use those decadal values, and there is they're basically using zonal averages. So there's one value per latitude, if you will. And there's also a seasonal cycle, because that's important. And that is the case also in that pre-GFED years. So here we do see zonal averages that evolve with time and have that seasonality. Once we get over GFED, then you have really like local, localized emissions. And then in the future, it goes back to being these zonal averages with that seasonality that doesn't change with time. Yeah.
It seems like a really large jump in like how idealized your representation is, and I wonder if there's some middle ground where, I mean, we know more than nothing about where these emissions are coming from. Like, could you have some sort of representation that at least, like, the smoke is coming from Alaska or the Canadian Shield, and at a certain season, and it's going to move, like, at this rate following the predominant winds?
Yeah, yeah.
It's surprising that there's so little of that going on.
Yeah.
And then it makes more sense why it has such a big impact to all of a sudden hit it with
Yeah,
sort of high.
I think you're right, and I think prior to GFED, our understanding of where those emissions were coming from is a little bit limited. And something that I kind of glossed over a little bit is that the regionality of where these high and low fire years are happening is important. If you have a fire at 40 North in China, it's not going to have the same impact that if you have it in Alaska, for example. And so I think adding that regionality prior and after, you kind of get into a little bit of shaky territory, because as I said, that location can have a big impact on where that response is going to be. So you kind of have to be careful about that. But I agree that it is a big jump in the way those are inputted. Yeah.
And then another question is there any attempt to differentiate like wildfires from biomass burning that's purposefully done? Because there are some places that use that as an agricultural practice, and there's a lot of biomass burning that is human generated,
Yeah.
and then like we have a lot more control over versus
Yep.
a wildfire.
Yeah, so I'm not an emissions expert, but my understanding from what I've looked at is that the model differentiates between forest fire and grassland fire. And there's also anthropogenic biomass burning, which again kind of relates to, like you say, like changes in land use and things like that. This is only the non-anthropogenic part, and it includes both fire and grassland fires. But yeah, there's also that part to be considered.
I'm sorry, I just want to follow up on that. When you say the non-anthropogenic,
Yeah.
so the anthropogenic being like just general distributed emissions, or anthropogenic meaning human-caused wildfires?
Anthropogenic meaning human-caused emission, yes. And human-caused, I think land use change is how I think of it. So like when there's a forest that, the thing is like, it's not, it's slash and burn agriculture. And the thing is like, that's all prescribed. So there's actually very little evolution of that with time, whereas there should be, as we know, has been happening and is going to happen. But yeah, this is kind of like human-induced fires, or also there's also might be some biomass burning coming from like industry or industrial activities or things like that. Yeah. Yeah. Yeah.
I was wondering, like, what would be typical residence time of the particles involved with one such fire be? So, let's talk about this.
Yeah, absolutely. So when these particles are first emitted, they kind of stay in their hydrophobic mode for about like 3 to 4 days. And obviously the bigger particles get deposited very quickly, right? Afterwards, I would say that from what we found, they can stay in the atmosphere for on the order of like a season, maybe like a few months to up to a season. But again, then you start getting into like much smaller particles, and again, particles that have aged and that have changed chemically. But that's about the residence time of these aerosols in the model. Yeah. Yeah.
So for your diagnostics about the response, was that 40 north to the pole, or was that in the polar cap?
The mechanisms?
Yeah.
It was in polar cap.
Okay.
Yeah.
So to me, it seems like early on you showed here was the change in, here's the change in cloud condensation nuclei. It was in mid-latitudes for the most part. I'm wondering, and you showed at the end that a lot of the energy transport is in the atmosphere. How much of this is changes in circulation from the radiative effect of the biomass burning at its source?
Yeah, that's a very good question. And we found that at the beginning of GFED, so kind of when you have these first very high years, high and low years of apologies, we do see that the change in energy transport and heat transport to the Arctic is also equally important. Once you get into the later part of GFED, it gets hard to identify because your mean state has changed quite a bit. And so how much of it is due to these differences in emission and how much is it just due because the climate is different by that point, so because the two simulations start to diverge. But definitely at the beginning, it's important. Some of the work by John Fasulo has tried to look a little bit into that and show that there is a big contribution. Yeah, but this is definitely something we need to look into a little bit more. Some people have also argued that maybe deposition on sea ice and changes in albedo could play a role. We've looked at changes in albedo and they didn't seem to be very large. Unfortunately, the model didn't save deposition of aerosol on sea ice, so we couldn't look at that directly. But it seems like that contribution is small relative to the aerosol, the atmospheric energy transport and the cloud aerosol interactions, like you mentioned.
And then the second question, is anyone looking, so GFED is the EOS era modus. Has anyone looked at using like AVHRR to go back further in time to get more representative kind of evolution?
That's a great question. I don't know any of these people that work on making the emission data set, but that'd be great. I have no idea if people have looked into that. Certainly for CMIP, this has not been looked into.
Okay.
Yeah. Sure.
This is really interesting. It's all very cloud and microphysical cloud intensive. And I have to admit, I don't know what the state of the art is in global climate models when it comes to cloud, aerosol, and microphysical processes. Are we at the point really where we should trust what's coming out of these global climate models, or would you rather advocate for a series of observational campaigns that would either verify or refute?
Yeah, that's a very good question. And I'm also not a cloud microphysics expert, and so a lot of it has been me talking to people who work on that, and they seem to have confidence in it, so I'm going to rely on their expertise. But I agree with you that there's actually, I'm working on a proposal with people at UW at the moment to use more field campaigns and observations at sites like Allard or Barrow. What is Barrow now? Whatever. To look at maybe that deposition and that burden of aerosols to see if we're even like close to simulating the right amount, because you're right, maybe we're completely off, and maybe that's what is influencing the way the model is responding to that. That's a very good question. Yeah.
Thanks.
Yeah.
I was just wondering, so how large is the seasonal cycle compared to these variations? And then is there a seasonal component in your nonlinear processes where your saturation might be reached?
Yeah.
During the winter and not during the summer, and
Right.
so how do that?
Right.
That play in there?
So to answer your first question, the seasonal cycle is, I would say, about like maybe a third to half of that variability. So it's still very, important. Yeah, your second question about the seasonality, absolutely. I think you have to remember that most of the biomass burning emissions are going to happen in the summer when wildfires are occurring. There's very little wildfires in the winter. And that's why we focused on the summertime response. Also because then in the summer, in the Arctic, you get that light that can interact with those aerosols with the direct effect. But definitely the seasonality, just like I mentioned with the regionality earlier with Evan's question, I think the seasonality of like if you have it in June versus if you have it in September clearly must have an impact. Yeah, absolutely. Liz?
So you hinted at this in one of your slides that some of the CMIP models show this and some of them don't. And I realize this is a super tedious thing to do. But have you looked into like details of how those models, the aerosol-cloud parameterizations are put together to see if there's any commonalities? I'm very curious about that.
I have, and I got lost very quickly, is what I will say. I was like, okay, let's look at all these different atmosphere model and cloud microphysics parameterization, and then, well, yeah, if you've ever read a paper on that, unless you're working on that every day, very complicated. So I looked into it. I looked into commonalities between sea ice model, atmosphere model, and really wasn't able to find anything with my very surface level preliminary analysis. But yeah, that's a good question.
If I could just follow up on that quickly. How the heck did you figure this out with biomass burning? Like teasing out these kind of things versus calls is incredibly tricky.
Yeah.
What was the process that took you to biomass being the culprit?
Well, so the process is a little bit kind of like what I've explained, that once we figured out that it wasn't really the model physics that was causing this, those CSM2 CMIP5 runs, they're newly available, but at NCAR we've been working on them for quite a long time. So once I knew that it was a forcing, then I just started plotting a lot of forcing figures, started plotting a lot of aerosols and a lot of different things. And at first I was like, what the hell am I plotting? Like, you have like number concentration, you have burdens. I was like, what is the difference between the two? So yeah, a lot of learning and a lot of trying to find, the needle in the haystack. And then once I plotted biomass burning, I was like, whoa, okay, there's something here. We need to discuss this. But like I said, there's clearly other things that have changed that could be playing a role and deserves to be looked into. But yeah, that's how science works, folks. Sometimes you need to dig deep and you find something interesting that you weren't expecting. So yeah. Yeah.
So given that when the variability is, I guess, more realistic, the model produces a lot more cooling. I'm sorry, a lot more warming.
Warming, yep,
Right.
yep.
So are our models in general then, are they too sensitive for the aerosol to aerosol?
I believe CSM2 is too sensitive to aerosols, yes.
So if
However,
you were to have that realistically throughout the entire.
I mean, okay, I will put a caveat to that. I think part of it, let me go back to the, I think part of it is the change from no variability to variability. And the reason why I say that is because we also ran some experiments where we added this variability over GFET and we continued it over the future. And we were like, oh, clearly something's, the opposite effect is going to happen. Absolutely not. There was no difference. And so I think it's really like those first few years that are kind of like pushing the system in one direction, and then the system kind of stabilizes a little bit. But I'm not sure that if we had that same variability over the whole period that we would see significant warming compared to those. I mean, that's something to be looked at. I don't have an answer, with a figure for you. But my intuition is that it's really that change from low variability to variability that kind of, again, just kind of like pushes the system in one direction.
Question. This is out of my field. I'm really curious. I kind of anticipated that I would hear about the black carbon albedo changes, and
yeah.
turned out to talk about aerosols and cloud feedback. So I'm curious, is black carbon albedo change not that significant or relative to these other things?
Yeah, exactly. Like I mentioned earlier, we looked at that because we thought that that could be one of the ways that it impacts the sea ice. But like I said, the model simulates deposition of aerosols on the sea ice or on land, on the surface. It didn't save the rate of that deposition, so there's no way for us to really know, like, oh, there's that much more that got deposited on the sea ice versus that other simulation. But I did look at albedo changes on the ice and the snow, and we saw very little differences in that albedo changes. At one point when let me move forward a little bit, when the sea ice starts to be very different, we start to see albedo changes just because, the extent of sea ice that you have is completely different. But I would say that at the beginning, we saw very little impact on the albedo. So it seems like the deposition and that radiative impact is quite small compared to the cloud changes. Yeah. Yeah.
Have you looked at why there's difference between CSM1 and 2 on initial condition? You have to say, was it?
Yeah, so this is, there we go. This is something that other people in my group at NCAR have looked into. And one of the big changes between CSM1 and CSM2 is in the snow sea ice microphysics scheme. So it's a lot of details, but we went from the bits in the scum scheme to the mushy layer scheme. Whatever. All that means is to say is that we kind of model sea ice physics differently, and that seems to have that really big impact at the start. And we start just, another aspect is we start with a lot less snow. The atmosphere model also produced too much snow in CSM1. And so we have a lot less snow on the sea ice in CSM2. So kind of all these aspects led to that mean state difference to start with. Yeah.
You also have more biomass burden, right? No, I mean, even in before the GFED.
Yeah, before GFED, yeah, that's true. Yeah, absolutely.
Any other questions?
So for those two large ensemble, which one do you recommend to me?
That's $1 million question. Yeah, I explicitly did not put the observations on this plot because I didn't really want you to know where they were. Turns out they kind of fall in between those two simulations. I will say that, yeah, I don't know which one I would recommend. To be honest, I think the CSM1 starts with too much ice, but the rate of decline is pretty similar. It's actually a bit slower than observation, but this one is too fast, so they kind of have advantages and disadvantages. I mean, at the end of the day, I don't think the point of a model is to reproduce observations perfectly. I think it's more, you should use it more as a tool to learn about the physics and the science, and clearly with this, and the fact that they simulated very different Arctic sea ice, we were able to learn a lot of things. If they were bang on observation, we wouldn't be asking all these questions, right? So I don't know. I don't know which one I would recommend. Maybe depending on your application. Yeah, Evan.
So I'm really interested in your explanation of like the aerosol loading and how you start at a very low baseline, adding a little bit of aerosols changes the system a lot. I guess I'm wondering if you, like, does that hold true everywhere? And are, like, I can imagine that there's biomass burning happening in the southern hemisphere, and if there's places where the air is really, really clear, and suddenly you have these emissions causing a big change from a really, really low baseline. Do you see really big differences in that region as well? And would that impact Antarctica sea ice, for example?
That's a very good question. Actually, a colleague of mine just emailed me earlier last week about this, because as we all know, there's been some big wildfire years in Australia recently, and the sea ice has also been declining in Antarctica, which it was kind of increasing before. So I haven't looked at that, but I think that's definitely something I want to look into, because, like, are the processes similar and do we have that same impact? I think you're right that you need to kind of look at a region that is, like, kind of normally pristine to have that, you know, that impact, but clearly Antarctica could be another place where this would happen. Obviously, Antarctica is a little bit different, you know, the circulation around it, the way these aerosols get transported, and the sea ice also is very different. It's much thinner to start with, so maybe that the response is different, but that's definitely something I'm interested in looking into. Yeah.
Based on the residency of the biomass burning, do you know if there's any lag effect in fall and winter season?
That's a good question. I haven't really looked too much at the fall and winter because I didn't see large changes. I think once you get to fall, you start losing the sunlight in the Arctic, and also you're impacting more the growth processes. So yeah, I haven't really found something in terms of a lag effect, but there could be. Yeah, that's possible.
All right, let's thank Pat one more time.